Okay, today we're going to talk about solubility and factors that affect solubility like solute and solvent interactions, pressure, and temperature. So, as we start many of these lectures, let's focus on the vocabulary. What is solubility? And maybe you have a good idea what it is, but sort of the by-the-book definition is an amount of solute that can dissolve in a given amount of solvent at a given temperature. So, remember, in previous lectures, we've defined what a solute is, what a solvent is. We're talking about mixtures here, and it doesn't have to be solid liquid or liquid liquid. You could have a gas solute and a liquid solvent. All of these are mixtures, and solubility is a term that applies to all of them. That is going to tell you what is the maximum amount of that solute. So maybe it is sort of a prototypical leaning beaker here, apparently, of water that you're trying to put some sodium chloride in. And there's some maximum amount of these sodium chloride crystals that will dissolve in this water. And after a while, if you keep pouring the salt in, well, eventually, even if you stir, you'll still have crystals at the bottom. They won't dissolve. You are past that solubility or maximum amount that will dissolve. Now, the exact amount is a certain amount for sodium chloride, which will be different for potassium chloride, even something very, very similar. And it'll be certainly different for something like sucrose. So the point is that this solubility is very characteristic to the exact solute and solvent you're talking about. So there's going to be a different solubility for every single different mixture. And that's because it really depends on what kind of solvent it is. Here it could be water, where you have this lone pairs on oxygen and this negative charge, a dipole, and even hydrogen bonding that can develop with neighboring water molecules. So these are all intermolecular forces that we have to think about. So all of these interactions, whether it's a hydrogen bond, a dipole-dipole, or van der Waals force, all of those will affect the solubility. Other things that will affect solubility will be pressure and temperature. Okay, and we'll describe why each of these is going to affect solubility in the coming slides. But first, let's focus a little bit more on this first one here, this solute-solvent interactions. Now, you may have learned at some stage this nature of like dissolves like. Okay, why does oil not mix with water? It's because the intermolecular forces, oil to oil, nonpolar to nonpolar, is different than the water forces, polar to polar. And so when you mix something nonpolar like oil with something polar like water, they separate. They are immiscible, unmixable. Okay, so this rule that we learn at some introductory chemistry level, like dissolves like, describes that similar intermolecular forces between substances generally means solubility. Okay, so here we have a glucose molecule that we use in our body for energy. And you can see all these OH groups, right? Here's one, here's one, here's one, here's one, here's one. And they're all sort of dangling off the glucose molecule. So will this dissolve in water? And the answer is yes, because these OH regions are kind of like water's OH regions. And they can set up their own hydrogen bonding right here. So if you have a molecule like glucose that is polar, it's probably going to dissolve in a polar molecule like water. Okay, so a polar substance like glucose will dissolve in a polar solvent like water. A nonpolar substance like this is cyclohexane, there are no OH groups here. It is all, pardon me, hydrogen and carbon. And there are no sort of dipoles present, so it is nonpolar overall. So this will dissolve being nonpolar, this cyclohexane. Will dissolve in nonpolar things like oil. Now, in a more applicable case that you might deal with in your everyday life, we have these vitamins. There are fat-soluble vitamins, and fat here you can think of as an oil as a nonpolar compound. And so fat-soluble vitamins like vitamin A, why are they fat-soluble? Why is there solubility in fat? It is because the molecule is nonpolar, and nonpolar molecules will dissolve in fat or oil, this nonpolar compound. And to take a look at this, there is one OH group here. And so you could argue, well, won't this, dissolve in water because there can be a hydrogen bond? And the answer is there might be an attraction with water, but there are no attractions anywhere else with water. Okay, so while we'll outline it in blue, because water's blue, this might be a polar sort of group here. It is far and away outweighed by all this nonpolar area. So overall, the molecule tends to behave like a nonpolar molecule and dissolve in nonpolar substances. So this molecule, vitamin A, is important in making the molecule retinol, which is part of the vision process. And you hear a lot of times that, eat a lot of carrots, you need your vitamin A. And while that's true, there's this extra sort of conspiracy that extra carrots will make you a super seer, a super vision person if you just eat way more carrots than you need. And that's actually propagated by the British Air Force in World War II to try to distract German pilots from understanding the new radar technology that the Brits had. So that was sort of a conspiracy early on that extra carrots would give you supervision powers that was originated by the British Royal Air Force. So kind of a fun aside, but you do need carrots for this retinol molecule for seeing, but it's not like eating extra carrots will give you magical powers. Get your vitamins when you can from food sources. Okay, so that's fat soluble. If you eat way too many carrots, then you will have extra vitamin A stored in your body. Okay, and so over time, if you eat way too many vitamins, there is a chance you are overloading, say, your kidney or liver. Although I will say the vast majority of people aren't really in danger of doing that. Eat a well-balanced diet. That's the best advice. There's also water-soluble vitamins. And so this water molecule, it is H2O, is polar. And so the vitamins that tend to dissolve in this water molecule, which is polar, is going to have a bunch of OH groups, like vitamin C. Okay, so here's all these polar groups. All of these polar groups outweigh any non-polar regions of this molecule. And so overall, vitamin C is polar. And so if you are eating an orange and getting your daily allowance of vitamin C, and then you also go and take, 1,000 milligram pills or Emergen-C or Airborne or all these other vitamin C supplements, you're literally flushing money down the toilet because they're water soluble, which means any excess that your body doesn't need just gets excreted in your urine because they're water soluble. That's not necessarily the case with vitamin A. They're stored in fatty areas of your body and the liver, but anywhere there's fat. So you can build up extra vitamin stores in your fat, but water soluble vitamins like vitamin C, anything in a daily dose that's over what your body actually needs, you're just literally flushing down the toilet. So like dissolves like for solute-solvent interactions, this governs how much a certain vitamin or any compound will dissolve in a solvent. So let's pause there before we move on to pressure and temperature and think about whether each of the following substances is more likely to dissolve in carbon tet or in water. And think about these like dissolve like rules that we just discussed. So feel free to pause the video here and solve if you want. Otherwise, I'm just going to proceed and work it out. So the first thing you want to do in problems like this for whether a substance will dissolve, will it mix? Well, like dissolves like. Let's first think about water and carbon tetrachloride. Right? We've already said several times that water is polar. And the reason it's polar is because, well, each of these hydrogens is bonding to this oxygen. But this oxygen is a lot more electronegative, and so it tends to draw the electrons in this bond closer to it. And the same in this bond. Okay, the net effect here is that more of the electrons will lie on the oxygen, or more of the electron density, I should say, lies on the oxygen than it does the hydrogen. And so we represent this with a dipole. Sometimes you'll see these delta minus, delta plus symbols. So this is a dipole, it is polar. You can draw the same sort of thing for carbon tet, but it's important to draw the geometry. And this is a tetrahedral molecule. Go back and review the lectures we've done on molecular geometries and Lewis dot structures. You can add in the electrons around each chlorine, I suppose. It doesn't really matter for now. The point is, in this structure, chlorine is much more electronegative than carbon. And so while in this bond, the electrons are pulled towards this chlorine, and I'm actually going to erase these because writing Cl kind of looks like carbon with an extra pair of electrons or a bond. There we go. So the chlorine here is hogging the electron density away from carbon, but this chlorine on the other side is tugging back in its direction. And it turns out that these things are just enough opposed from one another that there's no net effect of the electrons being on the left or being on the right. Okay, that doesn't exist like it does here, where oxygen is hogging the electrons from hydrogen. So this counteraction from each of the chlorines dictates that actually overall this carbon tetrachloride is nonpolar. And so now the question is, which of these will dissolve in which of these? And it's like dissolves like. So now we go through and assign, is this C7H16 hydrocarbons always going to be nonpolar? So that should dissolve in my nonpolar carbon tet. Okay, iodine 2, the iodine molecule. Well, this is just two iodines bonded to each other. Neither iodine wants the electrons more, so this is nonpolar overall, and that will also dissolve in carbon tet. Let's look at sodium sulfate. This is an ionic molecule, and an ionic molecule is going to turn into two sodium ions and one sulfate ion when it gets dissolved in a polar compound. And the reason is you need these charges, or I should say, you need the dipole to interact with these charges more strongly. So sodium sulfate will dissolve a lot more in a polar molecule because you have these charges that can be attracted to this dipole, which is much more favorable. You can arrange all of these oxygens around these sodiums to give you a positive negative attraction. So these ionic compounds will frequently, almost always, dissolve more in polar compounds than nonpolar. So it's not right to call this polar or nonpolar, it's ionic, but the answer here will be it'll dissolve in this polar compound. And finally, HCl. The HCl molecule is polar. Chlorine wants these electrons much more than this hydrogen, and there's not like there's another force pulling on the hydrogen from the other side like there was in carbon tet. So overall, this hydrochloric acid is polar. And so these two in the middle dissolve in water, and the ones on the outside are both nonpolar, will dissolve in carbon tet. So that's using the like dissolves like rule, and a little bit about solubility and solute-solvent interactions. Now, there's two other factors, of course, pressure and temperature, that are going to affect solubility. How much of these solutes fit in a solvent. Now, this is mostly about gas. Okay, so pressure affecting solubility. We're thinking about a gas-liquid mixture. Okay, and the solubility of the gas is going to depend on how much gas there is, which seems obvious, but let's think about it from this vapor pressure point of view. So think about this glass or beaker, I should say, of water. Right, there's a bunch of water molecules in here. Now, they exist at some temperature. There is some ability for water molecules at the surface to go up into the gas phase. And if you close this container, these molecules will collide with the edges of the container and eventually return to the water. But this is a dynamic process. There's always waters going up and other waters coming back down. And that's what's trying to be shown here. in this phase transition more generally between a liquid and its gas. So in this closed container, there's constantly molecules going up to the gas phase. Here's some, here's another, here's a third one, but they bounce around and they come back into the liquid phase. Here's one, here's another, here's a third. Now, at any snapshot in time, you can think about the number of molecules that will be up here in the gas phase, okay? Now, this gas, its ability to enter the liquid and its preference to enter the liquid depends on how much gas there is up here. And so you could think of this as pressure. If you push down on the top of this container, right, and moved this container top down much lower, effectively what you're doing is making the molecules that are bouncing around in the container have much less space to bounce around. You've moved this top down to here. And so the molecules much more quickly return to the liquid. And so not just in a liquid going to gas, going back to liquid, but more generally for any gas above a liquid, the amount that fits in the liquid is going to be proportional to the pressure you exert on it. So in this sort of straightforward example, increasing the pressure by decreasing the volume means these molecules have nowhere to live in the gas phase. They go back into the liquid phase. But that's really just showing an example of pressure's effect on solubility. Okay, this comes down to Henry's law, a distinct formula for solubility, the pressure, and this constant. Okay, and each of these have unique units. The solubility is usually in a concentration unit like molarity, so moles per liter. A pressure P here is going to be in a pressure unit like atmosphere or maybe torr, psi, etc. And your constant here, K, this is called a Henry's law constant. And this is specific to each mixture. Okay, so this constant, which will have units of moles per liter times 1 over a pressure, either atmosphere or torr, right? So that when you multiply it by this pressure, you get the units of moles per liter back out again. But each of these Henry's law constant depends on the mixture. So it depends if it's nitrogen mixed with water or carbon dioxide mixed with water, right? Or oxygen mixed with water. It's very specific to that solute-solvent interaction, okay? The point here is that Henry's law says the greater the pressure, right? And specifically the partial pressure, the amount of gas up here, the better the liquid can handle that gas and the more solubility there will be. Okay, so this is how we carbonate beverages, right? With carbon dioxide, you pressurize that vessel, and a lot of the CO2 above the soda goes into the soda, and you cap it under that high pressure so that when you uncap it, you hear the hiss. Now, another sort of application of this is think about when we burn fossil fuels, and we're adding more and more CO2 to our atmosphere. Okay, the more and more CO2 we add to our atmosphere, the greater the pressure of CO2 is. And the greater the pressure, the greater the solubility, meaning the more of that CO2 will find its way into our oceans. And this leads to ocean acidification and the destruction of coral reefs. So let's look at an actual quantitative problem that is pretty straightforward, but sometimes students get confused with units. So feel free to pause the video here and practice this problem on Henry's law. Otherwise, I'll go ahead and solve it. Okay, so Henry's law constant for nitrogen at 30 degrees Celsius is 6 times 10 to the negative 4 molar per atmosphere. Right, you're always going to have concentration per pressure as your Henry's law constant units. What is the pressure of nitrogen at this temperature if the solubility is 0.0009 molarity? Okay, you just have to remember Henry's law formula. The math is very straightforward here. It's just about recognizing what is the pressure. This is what you're looking for. So the pressure I'm looking for is going to be the solubility divided by the Henry's law constant, and the Henry's law constant for nitrogen. Okay, I'm told here the solubility is 0.00090 molarity, and I'm told the Henry's law constant is 6 times 10 to the negative 4, which is 0.00060 molar per atmosphere. So here my molarity units will cancel, which is good, and I'll be left with 1 over atmosphere, which means the unit of atmosphere comes up to the top. And so my answer here should be 1.5 atmospheres. So over time, you tend to remember these formulas sort of automatically the more practice problems you do. So if you get, confused about remembering all these, it's really important to practice them, and you'll start to get some familiarity with them. And even if you don't memorize the formula, and I didn't give you this formula, think about what you're asked for. If you're asked for a pressure, and you have something in units of molars per atmosphere, and something in units of molar, well, if you have no idea what the equation is, just look at the units. How do I get a unit of pressure? I get a unit of pressure by taking this unit and dividing it by this unit, right? Which is the solubility in molarity divided by the Henry's law constant. Okay, that's how I get pressure. And amazingly, that's the exact formula I used. So don't forget to check this sort of dimensional analysis to come up with these formulas in a pinch. Now, the last effect we're going to talk about here is temperature. Pressure affects solubility. The solute-solvent interactions affect solubility, but so does temperature. Now, we're going to talk about solid-liquid mixtures and gas-liquid mixtures here. So temperature affects, for most solid, as temperature increases, the solubility increases. Okay, that is mostly going to be true. And you can think about this because, in order to dissolve something, the first thing you have to do is overcome this ionic bond force, right? So to get sodium chloride to dissolve in this water, you're going to have to be overcoming this sodium chloride attraction. Now, if you increase the energy of this sodium and chloride, you're increasing sort of the molecular motion of this sodium unit, atomic motion, I should say, and the atomic motion of these chlorines. So the more energy you're forcing these things back and forth with as you're increasing the temperature, the easier it is for them to split up. So most of the time, you're going to increase the solubility by increasing temperature. It's not always the case because you're balancing that with the diffusion of the liquid molecules in here as you increase the temperature, as well as all of these solvent-solute interactions that are trying to form when you dissolve something. Okay, so for most solids, as temperature increases, as we go to the right on this diagram, the solubility will increase. So here A, B, and C follows that trend. It's not always true. Some increase greatly, some remain relatively constant. There are a few that decrease, and it's not super important you remember which ones decrease and which ones increase, but the guiding rule here is that for most solids going into a liquid, solubility increases with temperature. So if you're trying to dissolve something like sodium chloride and water, increase the temperature of the water, and you'll find you get a higher solubility. Now, for gases, as temperature increases, solubility decreases. Okay? And here, there's not as many intermolecular forces that you're dealing with. Okay? This gas is pretty dilute, meaning it doesn't have a high density. That's why it's a gas. It's a low density thing. But as you increase temperature, you're increasing sort of the kinetic energy of this molecule whipping about in here. And you're increasing its ability and the frequency with which it reaches the surface. And the more it's at the surface, the more it's going to be leaving the liquid and going into the gas phase. So if you want the solubility of the gas to go up, meaning more gas in here, you actually want the temperature to go down because you want the gas that does get into here to slowly meander about and find it hard to reach the surface. And even when it reaches the surface, it's not going to have enough energy always to leave the surface and go to the gas phase. That's what this Maxwell-Boltzmann distribution suggests. The kinetic energy of these gas molecules is proportional to their temperature. And at high temperatures, there's going to be a lot bigger fraction of these molecules that have enough kinetic energy to enter the gas phase from the surface of the liquid phase. So for all gases, as temperature increases, the solubility decreases. And a fun application here is that cold rivers have higher oxygen content for the fishies than warm rivers. The warmer that river gets, the more the oxygen comes out and escapes to the gas phase and comes out of the river, and the sadder the fishies become. Another application, of course, is our oceans. And kind of like we were talking with pressure, our oceans can store a lot of carbon dioxide. And so all of this CO2 that is naturally being stored in our oceans, as our oceans warm up and get hotter and hotter, that encourages more of this CO2 to leave. And more of the CO2 leaving means there's more and more CO2 up here to act as a greenhouse gas, trap the IR radiation from leaving Earth, increase the overall global temperature, and lead to global warming. So, solubility, really important, affects a lot of our lives. We don't always stop to think about it, but hopefully in this video you learned something about how pressure, temperature, and intermolecular forces can affect the solubility of a gas or a solid within a liquid. So, that'll do it for this lecture. In future lectures, we're going to move forward into concentration, like parts per million and molality, and eventually get to colligative properties. So that'll do it for this lecture. See you next time.